lovely room. I'm already enjoying this. Okay, so anyone know what this is? Sorry for the very poor image quality. I think, yeah, I don't know what happened here. This was a better image at some point. Yeah. Do you know what this is? I have squint at it. Okay, so what this guy is doing is he's actually, so this is the ENIAC. The ENIAC was one of the early computers designed by John von Neumann. So he's changing something there that's probably burned, some vacuum tube or something that's burned out. Yeah. So this is sort of my icon for computing. This is the steam engine, which the steam engine was in some sense responsible for the birth of thermodynamics because it prompted people to ask the question, how do we make better steam engines? And the converse question, what are the limits? What is the limit beyond which I cannot improve a steam engine? And the human brain for me is stand-in for the idea that evolution leads to the emergence of sophistication. So it leads to galaxies coming together, leads to crystals, leads to origin of life, and so many other transitions in evolution all the way to sort of many wonderful sort of biological artifacts, including the human brain. So what I'm interested in is, so the human brain in some sense is a thermodynamic object. It requires energy to do its work, but it's also a computational object. So it seems that if we want to understand this notion of emergence, this notion of self-organization, we really should be dealing with the connections between thermodynamics and computing. Apart from the scientific motivation, there are many practical reasons to worry about the thermodynamics of information processing. The most direct one comes from sort of Moore's law hitting its limits, and then we want to understand how to dissipate less energy, what is the minimum we need to dissipate, ideas like that. But also if we want to build better sort of microscopes, better telescopes, we usually don't think of these as information processing devices, but that's what they are at heart. And understanding whether information can be used, whether energy can be used to do better information processing, do more information processing, is fundamental to a lot of the technology that we build and work with. That's why I care about this problem, and I believe there are sort of many more reasons to care about this problem, but I'm not. You may have your sort of own sort of individual reason to care about this problem, and I would love to hear it maybe after the talk if you tell me why you care about it. Okay, so let's start with something which is our common experience. Computation requires energy. So if you look at something made out of transistors on silicon, you look at a cell phone, the human brain, or some server farm sitting somewhere, computation ordinarily requires energy. Even if you're running something like a clock, you have a battery in there. So this prompts the search for an analogy of this sort, that maybe computers are machines that take in energy and output computation, just as steam engines are machines that take in energy or heat flow and convert it to work. So can we turn this analogy into some kind of thermodynamics of the computer? So can we ask, just like the question was asked, what is the absolute limit to the efficiency of a steam engine? What is the absolute limit to the efficiency of this kind of a machine? The answer for thermodynamics was given by Sadi Carnot, who came up with this notion of a reversible engine and proved that whatever engine you build is worse than this reversible engine, which was a mathematical construct. So can we somehow describe some idealized computing engine, which may not be possible in the real world, but that's okay. And can we sort of say that this will be the limit, that we can't do better than this? One of the first people to ask this question and sort of think along these lines was John von Neumann. And it's hardly surprising because he was very much involved in the design of the ENIAC. he took a lot of inspiration from neuroscience for the design, so he was very much conversant with what was going on with the brain, and he was, his first degree was actually in chemical engineering, so he knew his thermodynamics very well. So he tried to sort of understand this picture, and the way he made the connection was, he said, what is the cost of computing per elementary act of information? For the brain, we can say an elementary act is a spike, a neural spike, according to John von Neumann. Now, you may argue with that, you may say that there are much more fundamental events going on in the brain, which is, I think, a fair point. But this was, remember that this was in 1949, so we can cut him some slack there. So for the ENIAC, he said, so he did not exactly say what is an elementary act of information here, but he did some analysis on it, so we will get to it in a minute. So yeah, and here he described something he called the thermodynamic minimum, the minimum cost of doing information. And we will, so what did he mean by this? It is commonly taken that what he meant by it was something like erasing. He did not actually specify what he meant by it. So he was writing up these notes, and he passed away before he could, do full justice to all his ideas. So we have to guess at some point to what his intentions were. So erasing is an operation. So essentially, like erasing a board resets it, right, to all zeros. So think of black as 0 and white as 1. So the board is initially in some random state, random because you don't know what's written on it. And erasing sets it all to 0. Okay? So that's how we are going to describe erasing. In terms of physics, if I have a single particle in some volume in some available volume, sometimes this is called sort of a Szilard engine, a single particle of ideal gas in some volume, because a thought experiment like this was first considered by Leo Szilard. Now think of some kind of a dividing line here, which need not exist physically, but it's sort of a line you are using to make a decision about whether the molecule is on the left or on the right. If the molecule is on the left, call it the bit 0. If it is on the right, call it the bit 1. And the molecule by itself is sort of randomly moving around, so this bit is sometimes 0, sometimes 1, flipping around, and so on. And erasing means initially I don't know where the molecule is. I don't know whether it's on the left or on the right. And I'm going to erase, which means I'm going to make sure it's a 0 by compressing this gas. So one can ask, how much does this cost? So if you forget the fact that it's just a single molecule, don't worry about stochasticity, sort of take the usual ideal gas law, PV equals NKT and set N equals 1, then PV equals KT. So that gives P equals KT by V. So P equals KT by V. So P dV is KT by V dV. And you want to integrate this going from V to V by 2. Right? That's the work done. So you get KT log 2. Okay? This is sort of a fake calculation, but you can make this more formal in terms of phase space volume and compressing it and so on. And you can say the expected cost for such an operation will be KT log 2. Okay, so what we are seeing here is sort of a deeper dictionary between thermodynamics and information. And this sort of goes back to Leo Szilard, and it's usually called Landauer's principle. I prefer to call it the Szilard-Landauer correspondence because I think many of the main ideas were already there with Szilard. So what is the idea? So what I'm going to do is I'm just going to define a bunch of things, and I'm going to sort of show you a lemma which may either be completely obvious to you because you have seen it, or if you have never seen it before, it might be surprising to you. Yeah? And that lemma will give you a way to move from the world of thermodynamics to the world of information, and from the world of information to the world of thermodynamics. It's an equivalence. So you will see a connection between bits and batteries in some sense. Okay. So I could, okay, so let me just put down a few definitions on the board. So here is relative entropy for those of you who, so how many of you are seeing it for the first time? Is there anyone who's never seen it? Okay, good. Oh, you're seeing it for, okay. So this is a quantity that, so P is a probability distribution, Q is a probability distribution. And so Pi log Pi by Qi is some sort of distance between probability distributions. Yeah. So log of 1 over Qi sort of measures the surprise for the individual who believes in the hypothesis Q when event I happens. Okay. So Pi log Qi is the expected surprise if an event is happening according to Pi, and I'm expecting it to happen according to Qi. So if I subtract the expected surprise of the person who has the wrong hypothesis from the expected surprise of the person who has the right hypothesis, that's how much extra surprise this person gets. That's roughly the relative entropy.
So can I just add, it's usually, we call it distance metric, but it is not, symmetric.
It's not symmetric. It's really like a distance square, and in fact, information geometers will appreciate that it is a distance square. Yeah. So distance square doesn't have a triangle in it. Okay, so suppose I have a finite set of states, or it need not be finite, I'm just saying finite for now. So how does one develop thermodynamics? One says there is some Hamiltonian function which consists of some internal energy part and some kinetic energy part, right? Some potential and some kinetic energy. So let's say the potential energy is E. So if I don't know the state that the system is in, then there is some belief I have about the system. So some kind of Bayesian view of thermodynamics going back to James and so on. Then there is some probability P over the set of states that I have, and so the expected energy in that belief state is summation Pi Ti. So I'm calling that the expected internal energy of the system. And for entropy, I'm using Shannon's definition of entropy, Pi log Pi. It's my expected surprise on learning the state I, if the system is indeed picked from an ensemble of systems which are distributed according to Pi. Okay? And my expectation for the system is also the correct ensemble. And free energy is the basic quantity of thermodynamics. So internal energy minus kT times the entropy. And we can define it this way. Now, P is just some arbitrary distribution. I have not said anything about equilibrium. Okay? I've just said, give me some distribution, I can define a free energy for this. And so, yeah. Equilibrium is defined this way in thermodynamics. You have this, right? So what I'm doing here is I'm abstracting out a lot, right? So these are all definitions you see in thermodynamics, but I have not said anything about thermodynamics. All I've said is, give me a set of states, I'm defining some quantities, some probability distributions and this, right? So any theory that gives you this set of states and defines these quantities, the lemma that I'm now going to show you will hold for it, including theories, various theories of thermodynamics. Okay, so here is the theorem of, if you take the free energy at some arbitrary distribution P and subtract the free energy at equilibrium, then that turns out to be kT log 2 times the relative entropy between P and pi. And this is a two-line calculation. It's not at all, it's at some level it's trivial, but at some level it's profound. Because it's saying, think of this as the number of bits you are erasing to go from pi to P. And for each bit you are erasing, you are increasing free energy by kT log 2. Okay. So the notion of this kT log 2, this erasing a bit, this idea is deeper than just for that single gas. Right? You can think of taking any system out of equilibrium as an operation that will cost you at least kT log 2 times the number of bits you are erasing. So dp relative to pi is the right way to count the number of bits you are erasing. So
how many of you have seen this theory before? Just for my
So just if you take this page, you write it down, you try to prove this, I promise you it is going to take you less than 10 minutes to prove this. It's the simplest, it's just algebra, it's just moving things around, it's not hard. I may have a proof on the next slide, but okay, so this gives us a dictionary. So free energy minus free energy at equilibrium counts the number of bits erased. So energy and information you can move across using this, and batteries and bits are the same, because batteries will store free energy, bits will store, so bunch of zeros, right? A bunch of 0 bits. If you know they are 0 bits, then by allowing them to randomize, what you are doing is essentially allowing a gas to expand and lift a weight. Yeah, there is an equivalence between the two. Okay. And so I have a pedagogical sort of article on this, which also gives the proof if you want to look at it. Okay, so what did von Neumann say? So he took the thermodynamic minimum as KT log 2. He didn't explain why he took it as KT log 2, but maybe he had erasing or something like that in mind. So people have speculated. So he took this number for how much energy does it require for a neuron to fire 10 to the 9 molecules of ATP. And he took this number for how much energy it requires for a vacuum tube to work. And he said, this gap I can understand, because we have just started making computers, nature has been at it for a long time, and we are quite lousy at it, we'll get better at it, and that happened through history. So we are now sort of maybe much closer to this, right? We still think neural computing is energy saving, but we are not as far away as we were in the 1940s. But this gap, he was surprised by. So here is what he said. He said it's missing a large part of the story. Even if you think that what he did here was an overestimate, there is more computing going down, you're not going to get 11 orders from it. So he said the thermodynamic analysis is definitely missing a large part of the story.
Do you know what's the sort of latest, sort of the most advanced technology locates within this graph right now?
Oh, you mean, okay, so we can look at maybe a very low, so you can look at DNA replication inside a cell. Okay, that's going to take 1 ATP molecule.
One?
The limit, 1 ATP molecule, that's 20 KT, right? So 20 KT versus log 2 KT is still about 60 or 70 or so. And I'll show you that I'm going to formulate the problem somewhat differently. It's not just going to remain a question of okay, you'll see. So give me 2 slides. Okay.
So this 10 to the 9 ATP is actual potential firing. Is that the definition? Because that's an integrated function. So technically there's a few more things going on, right?
So here's what he did.
Yep.
He, we know the energy bill for the brain,
yep.
right? So whatever, 30 watts or something, yeah. We can divide it by the total number of neurons, okay? So you
without
can
knowing
ascribe a
firing
number.
rate?
Sorry?
But to make your sense, what you said makes sense. We need to know the average firing rate of the neurons.
So this is what he did. That's not how he did it. So he did. Okay. So how did he do it? He you know the energy bill, you know the number of neurons, and he took some number for average firing rate, and he sort of came up with sort of per firing this is the cost. Yeah. So there is a time scale issue.
These are not, I mean, we wouldn't expect
it was a back of the
exact calculations, but rather a guess.
Yeah, on the order 1 to 100 hertz or something.
It was a back of the envelope calculation. Yeah.
Okay.
And he being von Neumann, he was smart enough to know that, he didn't know what this gap was due to. But he had some interesting speculation. He said maybe it's due to a desire for reliability of operation. So future work by Charlie Bennett and so on actually even started to question this lower bound, right? And push it down even further, which doesn't solve this problem, but maybe exacerbates it even more. Yeah. Okay, so I want to bring in timescales into this. So reliability is about timescales. Yeah? There is another timescale which is speed. how fast do you want to erase? So if you think of it in this sort of physical model of compressing a gas, if you try to compress a gas fast, what happens? It heats up. If it heats up, its pressure increases, it pushes back more, you have to do more work. Okay? So this calculation is an equilibrium calculation. So if you do it isothermally, right, you move it so slowly that it's always at equilibrium. But that's not the case in computing. We want to do things fast. We want to erase bits fast. We want to move bits fast. What happens if you do that? Okay? So we can build a linear model for what happens if I try to erase something fast. Let's have some erasing time in mind. We want to erase within time tau sub e. How much does it cost to erase a bit fast? So this is our model. There is some temperature inside. Now this temperature is a function of time. There is some temperature outside which is fixed. That's the temperature of the heat bath. There is heat flow from the outside, from the inside to the outside, and we will use a linear model for this, so called Newton's law of cooling. So what that means is that dq dt looks like some proportionality constant sigma, so coefficient of heat conductivity times the temperature difference. And now what happens? Now if I try to solve the problem of how I should compress, right? The question is, what should be my pressure profile? We can solve this problem. It's an optimal control problem. And in fact, a similar question was asked by Salomon and Nitzan in 1981. They were not interested in the cost of erasing. They were practical engineers interested in power plants and other thermal processes which have to be completed in finite time. And so they set up this problem and they solved this problem. It's a very nice paper. I would encourage you guys to read it. And this is what the answer falls out if you take their answer and you specialize to our case of erasing a single bit. This is what it looks like. And if you graph it, this is what it looks like. So in the equilibrium thermodynamic limit, you get kT log 2. As time becomes more and more precious, you sort of get an inverse dependence on time. And then there is a critical time that you absolutely have to spend, and you cannot do it faster than critical time. Okay. So we are doing all this to gain intuition. I have not yet come to my approach. I am sort of helping you sort of understand where the difficulties lie and where the opportunities lie before I get to my approach. Okay. So what I don't like about this solution in our context is that the answer depends on sigma. But sigma is not a fundamental sort of constant of physics. It's something specific to the technology we are using there. So in the limit, as I tend this coefficient of heat conductance to infinity, I have a vessel that's perfectly coupled to the heat bath, and my timescales disappear. So the gas is always at equilibrium with the heat bath because it gives out heat so fast. And then if I put sigma as infinity, this term disappears. I'm left with kT log. So I don't get something that's fundamental here. I only get something that's technology dependent. Okay. So I'm going to introduce the notion of reliability. So I'm going to say there is this time scale, but if I leave this molecule by itself, right, this bit, then it's going to be moving around. At some point, I won't know where it is. It may have gone to the other side, it may be here, I don't know where it is. Right? So there is a time scale for which a bit is valuable to me. So every bit has this property. So if I have a very flimsy bit, it has a short time scale. If I have like something written on a rock, put down somewhere, it's going to last 1,000 years maybe. So it's going to depend on the thermal environment around it also. But fixing temperature, so I'm doing everything sort of fixing temperature to try to make some progress here. Yeah. So I'm going to call this the reliability time scale. And my question is, fixing this, how much does it cost to erase a reliable bit fast? Okay. So now you can appreciate that copying DNA, is maybe a fundamental operation. Maybe it only costs 20 kT, but it's also a slow operation, much slower than what a computer here is doing with bits, right? And so so you can appreciate that this would cost more, but if you do the calculation, you try to figure out how much things should cost. It's still, we are not getting any intuition from just the equilibrium results about how much things should cost. We need to somehow get an answer that depends on these numbers somehow. And we can try to guess at an answer. What would be a good answer in terms of these numbers? Anyone? So some answers are clearly going to be stupid. Some answers have a chance of being right. So what would you expect for the dependence on tau r? This is a quantity that can grow exponentially with increasing height of barrier.
So if it's harder to array, it should be longer. It should take longer. It should be harder, more costly.
So you expect a monotonic increase with tau r. Okay? You expect as tau e goes down, you expect a monotonic increase. Okay? And it has to be, the dimensions have to go away, so it has to be a function of the ratio. Maybe there are some other terms, but at least this has to come in somewhere. And then what do you expect the answer will be in terms of this? Can it be linear?
That's what I thought, but
Linear is too big. So if I have a barrier as big as, say, the Himalayas or something, right, then tau r is exponential in the height of that barrier. So it says I'll never be able to cross that barrier in sort of a fixed amount, in a reasonable amount of time, which is false, right? We know it's false because we have done it as human beings. Yeah? So it's not linear.
I'm going to guess that's a log 2.
Let's try a log. It seems to scale well. I mean, this is just a guess. I mean, I'm not saying that's going to be the answer. It's just we are playing a game at this point. Yeah? Okay. So now let's make a model. Let's see how far we can take it. Yeah. So what I'm going to do now is sort of, so there is a way to do stochastic thermodynamics on Markov chains. Okay, it's sort of a well-developed field. It's called stochastic thermodynamics. I'm going to take the minimum I need to do this calculation right now. If people are interested, after this talk, I'm happy to sort of take you through stochastic thermodynamics on Markov chains in detail and show you how it works. And yeah, but for now, I'm just going to quickly do these things. Okay, so this is a two-state Markov chain. The rate of this transition is K01, K10. This is the dynamical equation. Probability of being in state 0 is, this is the outflow from here, right? P0 times K01, and the inflow here is P1 or 1 minus P0 times K10, right? And so the probability is balanced by this. Okay. I'm declaring the reliability time to be the time scale for this solution, right, to go to its equilibrium. And so that turns out to be this, right? If you write down the solution, there is an exponential and exponential minus t by something, and that something is this. And this is the stationary distribution, and this is the time evolution, right? Where this is minus t by this. So it's going to equilibrium at an exponential rate times the deviation from equilibrium. Okay, so here is how I'm going to formulate the problem. Okay, maybe I should back up a little bit. So, no, I shouldn't. Let me do it first and then I will. Yeah, so this is a situation where the dynamics is according to the system itself. I'm not doing anything to it. Here I am applying a control to the system which is causing the rates to change as functions of time. So there is a function u01t, there is a function u10t. And I have a dynamical system here, and I have a reliability time scale here. I have a different dynamical system here, and what I want my control to do is if I start at P0, the same distribution as on the left, then at time tau sub e, I want the probability to be 1, right? So tau sub r has appeared, tau sub e has appeared, and now my question is how do I pick u01 and u10? Right? So u01 and u10 must be functions of time so that the solution is feasible, right? So that this happens. In addition, there will be a cost that I will assign to it, and I want to minimize that cost. So yeah, I'll make a simplifying assumption that K10 and K01 are 1 and P0 is half. It's not necessary in the paper I solved the full case, but for now we will do this. Okay, so the question is how much does it cost, right? So I have to describe the cost. So here is what one would usually do in stochastic thermodynamics. One would assign a cost for raising a potential at a place where there is probability that the particle will be. And the cost will be the amount of probability times the amount you raise. So that's an expected sort of work done by the control. So let's first see what happens if we follow the usual thermodynamic prescription. Yeah. Okay. So if I transition from, okay, so this looks like U10 by U01. Let me get this right in my head. So that's going to be sort of the heat given out when I transition from this state to this state. Okay. So that's how much more energy there is in this state than in this state. And so I'm calling this delta E1. Okay. So here is what my control is going to do. My control is going to raise this by small amount h. If I raise this by small amount h, that puts the condition that h equals kt log of U10 by U01. So now I don't have any other constraint on these rates. As far as thermodynamics is concerned, the way I am doing things, I don't know how to constrain these. How does the rate change? If I have a system that's mixing at a certain rate, if I slightly increase one side, one would expect the rates also to be close to the old rates. But as far as the equations concerned are showing me, they don't constrain the system in that way. And this is a problem because it lets me cheat. It lets me cheat by making these rates as big as I want, because the cost is only dependent on their ratio. So I will raise this by height h and send these rates to infinity, as close to infinity as I wish. The system will mix very fast. This is the same cheat as sending sigma to infinity in the case of, because it's exactly the same, because I'm sending u's to infinity now. So I stay here for some time, very small time, and then once it has mixed, I go to h more, h more, h more. So essentially I can redo the isothermal, the equilibrium control here, and I'll get exactly the equilibrium cost for the work done, which is going to turn out to be kt log 2 plus an epsilon that I can make as small as I wish by taking the appropriate quantities to 0 and infinity. So I don't get anything, even though I have thrown in timescales into the picture. If I fix how much I can increase u, or if I put some artificial restrictions, then I can get something here. But it will depend on the numbers that I have fixed. It won't be a natural answer, it won't be a limit to the system. Okay. Yeah. So the point is, in the limit, it doesn't depend on tau r and tau e. So you don't get any trade-off. Yeah. And it seems wrong. It seems like just by raising it a little bit, I should not be able to choose arbitrary rates that are completely different from what went before. Yeah, any questions?
So is that the only solution to this? Or the only fast solution?
Well, I mean, the way I formulated this, the way I follow through on this is what we get. There is nothing else. So here is what I want to say. Here is where I see the problem as being, right? So there are two things. One is the work done by a control, and another is the cost of the control itself. They are two very different things. If I take this chair around the room and bring it back here, and you define work as force into displacement. Displacement is 0, work done, net work done, you might say, is 0. So can you talk about sort of how much, what is the cost of implementing a control to take a system along some trajectory without looking at the actual control, just looking at the trajectory of the system? Okay? Of course, if you look at the control along with the system, you look at the coupling, you can look at the joint system, you can look at how much the free energy of the control has gone down, and that's a meaningful way to talk about that particular interaction. But are there general principles where we can talk about the cost? How much must the battery on a control deplete for having to take my system through some trajectory? Okay. And it turns out this kind of formulation doesn't get at, it just gets at sort of work and heat dissipation, doesn't get at the cost. So I'm going to propose something new here. So before I propose, I want to introduce one sort of idea which is sort of familiar to physicists but maybe not familiar to everybody. So the notion is that of path space. So a path is literally a path, right? So it's you fix a bunch of time steps or you fix the entire interval depending on whether you want to do discrete or continuous. Right? If you do discrete, you can get away with probability theory. If you want to do continuous, you need your measure theory hat on. Okay, so path space is the set of all maps from T to 0. That's exactly what it is. It's just paths. So each path in this space becomes one of the points in this space. And so if you consider a path that starts at I0 and then jumps at, since I only have two states, I only need to tell you what are the times at which it jumps and where it starts. Right? Starts at I0, jumps at these times. Okay. Then I'm going to define a probability measure on this for the control U starting from state P0. Okay. The probability measure for this path is going to be given by something like this. So if I want exactly this path, it jumps exactly at T1, T2, Tn, then that path is, it's zero probability. It's a zero measure event. So I want to broaden each of these slightly. T1 plus dt1, T2 plus dt2, Tn plus dtn. So the probability for this set of paths now, right, this measurable set becomes probability of starting at I0 at time 0 times probability of not jumping from time from the first time, right, T0 to T1, this is the probability of not jumping. And then within the next dt, jumping from the state I am in to the right state, and then keep doing that again and again and again. That's your probability. So this is how you put a probability on path space. You put a probability measure on path space, which can give values to sets of paths. So this is going to be my cost function. So I'm taking this measure which I defined on the previous slide relative to this measure where instead of U I'm using the passive dynamic scale. Yeah. So in words, this cost is the number of bits erased in path space. Okay. So people have used this kind of cost a lot in control theory. It's called the KL cost, and people use it there for what they call as risk sensitive control. If you want a control that will do something and be robust to noise in some way, it turns out minimizing this function is a good thing to do. But nobody has claimed any sort of thermodynamic meaning to it as far as I know. Okay, so this sort of counts number of bits erased in path space. So I like to sort of say that this is some kind of path space Szilard Landauer principle, right? Instead of counting number of bits erased in phase space, which gave us equilibrium thermodynamics, we should be counting number of bits erased in path space. That's the norm. And in fact, looking at this kind of a cost function and trying to minimize it goes back all the way to Schrodinger, and he was thinking of this actually for some reasons motivated by quantum mechanics, but he was thinking of this in the following way. Suppose I have observations at time 0 and at time tau. Okay? So I know the system started in sort of equal probability for 0 and 1, and at time tau it is definitely in state 0. I made an observation and I saw it then. Yeah? So now what is the measure on path space? Given I know the dynamics of the system also, I know that it has some dynamics. What is the measure on path space that best explains these two observations? So now I have to condition my measure not just on the past but also on the future, because I have got some information from the future and I have to solve this problem. He showed us how to solve this problem, and in fact he showed that to solve this problem you will end up minimizing a cost like this. Yeah? So this is a large deviation rate function in some sense. So given that something has happened at 2 points of time, what is the dynamics in between to explain the least unlikely way by which that unlikely thing happened? And that dynamics is given by minimizing this relative entropy and solving for u. That will give you the path. Getting across? Okay.
Astonishing compared to what, or?
Oh, so I mean, not compared to it. So it's, see, every observation is astonishing if you have a large state space.
Okay.
Because, I mean, if I don't know, where something is going to happen, right? If there are like 1,000 boxes and I have like equal probability over all of them, and then one of the boxes is the event that happens, my surprise is going to be big. That's all. Right? So something has happened. So he just has an observation, and so the very fact that something has happened is itself surprising. It's not in comparison to anything. So now that I know this has happened, I should condition not just on the past but also on the future. And so I shouldn't follow the forward dynamics, but I should follow a dynamics that's conditioned on both ends. And if you try to solve that problem, then the probability of the set of all paths that do that give us the right solution, sort of goes down as the exponential of this relative entropy. So it's some kind of a Sano's theorem. It's a large deviation rate function.
So up there, UK is the dynamics under just our prior.
This is the passive dynamics.
The passive dynamics. So
leave the system by itself,
yeah.
and this is the controlled dynamics.
And so the passive dynamics are fixed but arbitrary. They're just given. They're our natural.
They are the natural dynamics of the system.
And then U are the controlled dynamics, and so the U themselves are a function of time.
Yeah.
Yeah. And so the controlled dynamics then both introduce path space measures.
Yeah.
Yeah. And so that's basically kind of saying that if that divergence is low, then our control looks a lot like the natural system.
Yeah.
And if that divergence is large, then it doesn't look like the natural system.
Yeah.
And so least astonishing in that case would be like the thing that kind of explains our final observation, but
deviates as little as possible
from the natural dynamics.
So in some sense, I only take those paths in that probability. So think of every path as some kind of a pipe with some water flowing. I would like to have the same amount of water flowing through it. Not more, not less. And whenever I deviate, I try to deviate as less as possible over all these pipes. And that's actually this is the same. So what Schrodinger did was also, so I mean there is a huge literature in a field called optimal transport, and this is exactly the problem that they solve. They try to move something somewhere else, right? So there is some mounds of sand at one place, and at the end of the process they want mounds of sand at another place. The question is which grain goes where? How do you transport it? And so the answer turns out that you do something like this. And yeah, so there are sort of multiple ways to think of this, but essentially this is what it is.
Yeah, so it's effectively a principle of least action. It's effectively a kind of principle of least action where this relative entropy is your free energy.
Exactly. So this is the usual, second law of thermodynamics written in terms of entropy production and free energy. So work done, some of it goes into increasing free energy and the rest of it goes into entropy production. Turns out entropy production is also a relative entropy, which there are it's a very it's a well-known calculation, but I have repeated it anyway in my paper if you want to look at it. So it's this relative entropy with respect to something called the time reversal of this measure. Yeah? So how does what we have used, right, this relative entropy cost, how does it compare with a formula like this? So we get something that looks actually quite similar in some ways. So this is free energy, this is still free energy. Ignore all the KTs. This is UP relative to UP reverse, this is UP relative to KP reverse. So this is the only difference here. u versus k. So we are using a different measure for time reversal. So it's as if the system doesn't remember that the control has been applied. Okay. So this is the only difference, but it has consequences. So the way we prove that, so the second law can also be said as this quantity is non-negative, entropy production is non-negative, or delta W is greater than or equal to delta F. All of that still hold here. This is non-negative. Delta of our new W is greater than or equal to delta F. Okay? But what we lose is this work is always non-negative. It's never negative. And in some sense that makes sense, right? If you're trying to make a system deviate from whatever it's doing, then the control pays for it. Okay? So maybe so this is not talking in some sense about recovery of energy. Okay, so this is our sort of setup now to solve this problem. So we want to find the optimal control, u star function of t, which will minimize this measure, such that the marginal of this measure at time tau e equals 1, 0. Right? So that means it has successfully erased at tau e. Okay. So we can do this by dynamic programming or Hamilton-Jacobi equations, whichever one is familiar to you. So you write down some cost to go function, and it's defined as VIT is how much more do I have to spend if I know that I am at state I at time t, right? So that at time tau e I am at state 0. Right? So VIT is how, in some sense, how happy I am to be at state I at time t, or unhappy. VIT, the larger it is, the worse off state I is at time t. And I want Vi of tau e equals 1, Vi of tau V0, right? I want to be at state 0 at tau e, so, and I put this to infinity. And I can write down a backward recursion, which is essentially how is V0 at time t related to V0 and V1 at time t plus h, and how much do I pay in terms of going from time t to time t plus h, right, by applying some control. And what is the best control to apply comes here as a parameter. We can take the limit as h goes to 0, make this a differential equation. It will be a non-linear differential equation, but there is a change of coordinates, which will make this into a linear differential equation with a closed form solution. This is unusual for a Hamilton-Jacobi equation. It just turns out this form of the problem is so nice. It's really just statistical, classical equilibrium statistical mechanics, but applied in this unusual sort of space, path space instead of phase space. And so the solution you get in the end is actually a Gibbs distribution. So it's really, it's maybe not, it's not obvious that it's the same, but at a fairly abstract, from a fairly abstract point of view, this is just equilibrium statistical mechanics, but done on path space instead of phase space, and you get a Gibbs distribution kind of answer. Okay, so this is the answer we got. Doesn't look like a ratio of logs, but it's greater than log 2, which is good news. If I send my erasing time to infinity, or my reliability time to 0, or the ratio to infinity in some other way, then it goes to log 2. This is the equilibrium thermodynamics limit, which is good. And if so realistic bits are not going to have this property, rather tau r is going to be much larger than tau e. When I do that, when I do a sort of Taylor series expansion and ignore terms that are of sort of second order in tau e by tau r, this is what I get. It starts looking like this ratio. Okay, so how much time do we have? Okay. Yeah, so what have we done? So we have formulated this problem of erasing in terms of this cost speed reliability trade-off, proposed use of KL cost, and obtained some answer. Now what remains to be done? Does it have a thermodynamic interpretation? So there are some, some things nice about this. There is sort of this Gibbs form, there is path space Landauer's principle, there is this probability theoretic, idea that I'm paying for pushing stuff on unlikely paths, right? So it's a large deviation rate function. So so I pay for doing things that would not spontaneously occur. And there's this information theoretic interpretation where I'm replacing this u by k, and that's the only difference. But what we don't have is sort of reconciliation with the other picture, right? Where I look at a system and a control together, an arbitrary control, right? And it gives me, so here right now my u are somewhat mysterious. It's not clear how these u's are actually applied to a system. So if I take a system, I take a control, I take a joint system, then I see how that u is applied, and then I compute how much cost is required to produce a certain control. Then can I lower bound that cost by this cost? Can I say this is a lower bound? Okay. So that is something we are still working on. We have not disproved it, but neither have we been able to confirm. Thank you.
So, how much does this result rely on your assumption of this thing being a Markov chain? It seems to me that this would work just as well for any process, as long as you can define a measure on the space of trajectories. In the kind of natural case and then the control.
So I have used the Markov chain assumption to solve this.
This particular case, yeah.
No, I mean I've used the Markov chain assumption to solve the Hamilton-Jacobi equation, because that's what gives me the recursion and allows me to solve it. The proposal that this KL cost should be the cost. Okay, so there is. So let me answer it in a different way instead of directly answering this. So physicists usually think of Markov chains differently from engineers. So let me kind of emphasize this a little bit. So there are sort of physical systems. Right? So you've taken some system now, you've fixed your coordinates, and everything else you're calling the environment. So in this state of physical system, you're thinking of some systems as Markov chains. Okay, this is the usual physics way of thinking of Markov chains. But engineers often have a choice on what they call the system. So if a system is non-Markovian, they are allowed to look at what is the memory the system needs so that it will become Markovian, augment the system with that memory. So look at sort of a larger class of systems which are Markovian. Okay. So there is this curious thing, no, that systems that are non-Markovian seem like a superset of Markov chains, but they are also a subset of Markov chains. In the sense that I can enlarge my space and make it a Markov chain. Right?
Although the enlargement is not unique to X.
It's not unique, but one would desire that it should not depend on the choice of enlargement.
Physics is a physicist. Physics is a physicist.
Yeah. So the point being that let's talk more about it.
So what's the intuition behind, like you presented one example which was the pre-Markov version and then this Markov version. And maybe like it's still mysterious to me just because it's subtle. Like what's the intuition behind the difference between those two cases? And what is it that the path space interpretation preserves that the other one doesn't?
Yeah, so both were Markov chains. There was it's not the Markov assumption that suddenly solved things. Okay? I had a problem even with the Markov assumption with the usual traditional thermodynamic work function.
Yeah, no, so that's what I'm not.
So what that allowed me to do was cheat in terms of the ratio of the rates. Right? I could send uij by uji all the way to infinity. So long as the ratio remained the same, I was not paying anything. Now, if uij deviates from kij, I pay for it. So if you look at the cost function, right? Maybe that way. This is my control, right? What appears here is the ratio. That's what is related to my cost of a jump. So my cost to go function, the difference here is related to the ratio uij by kij and uji by kji. And in particular, uij by kij at the optimal control equals kji by uji. So you actually get that the product of the rates remains the same, which is probably too nice for real controls, but we are not claiming that this is a real control. I think what we are claiming is something like a channel capacity theorem in Shannon's world. So we are sort of saying this is a lower bound to the cost.
And so it is kind of like, if you're not bound to the natural dynamics throughout time, then you can just do arbitrarily weird stuff at the start by playing with your ratios or whatever. And so having that cost in part space means that you pay for you just pay for significant deviations from like it's the natural.
I don't know. I mean, there might be other ways of solving this problem which are not going through the scale cost, which may, but you will need to introduce some axiom that will disallow both of them arbitrarily increasing and only the ratio coming into the picture.
But like both of those increasing creates very unnatural paths, right? Because then if they were both very high, you'd just be like going back and forward almost arbitrarily. Yeah.
But how do you capture that other than the way I have done? I don't know any. I mean, there might be other ways, but I haven't been able to.
Maybe one thing that's worth mentioning is that, like, I think the other problem is just that condition becomes a little bit unphysical because as both of those go very high, you're switching between.
Yeah, so I agree with the criticism that what this control achieved seems unphysical. I mean, I think that's something
because
that
it starts like
many of us
radiating
will
energy.
agree.
Like once it started switching back and forth, like as both those go very high, it starts switching back and forth at like terahertz.
So I think,
radiation
I think
comes
that criticism is fairly non-controversial. Everybody will agree that you shouldn't allow these rates to go completely different from the passive rates without paying for it in some way. But exactly how do you constrain them? I think that is not being clear.
I guess I was going to say if there was a kinetic energy involved as well, then that would take that into account.
Yeah.
Right, because you're effectively just the only energy, and this is the potential energy that's in there, and therefore you can shift it arbitrarily quickly.
Are you sure that? So all you would have is phase space. You would still have friction and noise, right? And okay, so now you would have a fluctuation distribution theorem. So if you try to increase friction, you would also increase noise or something. Is that? I'm not. So it will still equilibrate fast, right? If all you care about is equilibrium, it won't equilibrate fast because if friction increases, it will get stuck somewhere. Yeah, you're right. So yeah, maybe doing this in phase space might be another way to try to understand it.
So to build on what you were saying, could you please go back to the slide that was showing the path space measure? Actually no, sorry. Later with the cost function you're using. My apologies. Yeah. So to build a little bit on what you were saying, like the presentation of that control function, I guess, would have a lot of utility. Because as far as I understand it, maybe you have some thoughts on this. Like a lot of what we could say is that control could be a general policy. Like if we are some sort of like intelligent agent, like a robot.
I was about to say that, like, can you see the parallel between this and the usual, free energy formulations?
Yes.
So this is basically, an optimization problem where we are minimizing, as we say, surprises. So this is distance between, as actually you were started to say about like the posterior and priors. This is how we into the Bayesian inference. While I understand what you. So basically, this is distance between the posterior and prior. You are minimizing, and this is basically nothing but what we say about free energy principle, where we are minimizing the surprise. So and that's probably it. I mean, I was just really sorry. Probably you wanted to continue on that.
Oh, just very quickly.
Yeah.
But so if you reveal the rest of this slide, please.
Oh, there is just one more.
Yeah. In the sense that, and correct me if I'm wrong, but if we were some actor, like we're in a multi-agent system and we're an actor, one might then apply that to say, well, I observe you do something, and under my prior, I have many ways, kind of the natural measure of things you would do, you know, pick up a water glass, walk around in circles, whatever it is, and then on observing you do something, like standing on the side of the road looking left and right, I may then say, well, there is then a measure on policies that I would like to be matching your behavior that would constrain what I now believe how I believe you'll act in the future. And it makes sense that I want it to be as close as possible to the natural way I think things will behave, but informed by
the
your
difference here
actions.
is that you are only conditioning on the past because you only want your future policies to depend on it. But if you really cared about what happened in the middle, right? Suppose this is a situation of partial observation, right? So you only observed the other agent at time 0 and time tau. What the agent did in between matters to you. So you want to reconstruct it. Then the way you would reconstruct it would be to minimize this.
And so what are you going to say?
I was just saying that not specific to the way that you have set up the whole problem. So is it like we can look at it from the perspective like it's as a non-equilibrium steady state environment as well?
Not even steady state. This is sort of a prescription for non-equilibrium thermodynamics because as of today there is no prescription in non-equilibrium thermodynamics for what is the work, so when you are far from equilibrium, right? How do you sort of make sense of how much dissipation has happened? And so there is no sort of nice clean way to even talk about it. Like you can do sort of the linear approximation sort of.
But except with stochastic thermodynamics.
That's so even in stochastic, can you do it far from equilibrium?
I mean, you can at least write down a.
Oh yeah, so you can do the second order. Yeah, but I don't think people sort of seriously claim that is the time dissipate. So sure, so I mean you can say it's a it's sort of I don't know. I'd rather not say more. Better to.
So to totally change tack and ask a different question. Right now, computers are built to be reliable. There has often been proposals to make computers that are less reliable, but for example, if they were evaluating big neural networks, they don't need to be particularly reliable, and that could massively reduce their energy consumption. So does this theoretical bound, like are we anywhere near that theoretical bound now, and do you think it's still active? Like does it have a prescriptive element?
Yeah, so I think that this theoretical bound is definitely much closer to reality than anything else before, for obvious reasons, that there are no timescales. I have not, one obvious thing that I should have done is sort of taken 10 examples and calculated. I have not done that.
Well, that's something I would do,
I'd be very happy if you do it and tell me if it is consistent because I've never thought of doing that.
But a modern CPU seems very high, like unless a cosmic ray hits your register, you're pretty safe, like for hours, days, years.
Yeah, so I do think that as we better understand non-equilibrium thermodynamics, we will become more, or probability theory, we will become more and more comfortable with building more thermodynamic computers, which won't have just irreversible operations, but will go both ways. Right? And that is important. Going both ways saves you energy, but then you have to know how to deal with it. You have to know what is a realistic expectation. You can't ask for sort of reversible computer, zero energy kind of things.
I'm sorry.
I was just saying that there was there's a more practical like implementation of transistors who can, this is some work from people in Illinois Champaign, Urbana Champaign group of so they have these transistors where they can actually they're building on these transistors where you can actually do probabilistic. So it's not like 1 and 0 as usually we do, and that's the most, you know. So they are using intrinsic artifacts in the.
So this is actually a very big theme, I would say, within computer science. You know, we started off, the first computers were analog computers, and then we moved to the digital world. So now what we are doing is, you know, so probabilistic computing and stochastic computing are really where we are trying to bridge these two worlds. So the advantage of the digital world is sort of obvious. It gives us very good fault tolerance. The advantage of the sort of analog world is potential savings in energy and, you know, some kind of adaptive schemes that if I need more accuracy, I can sort of do it with more energy. If I don't need accuracy, I can pull back energy. And somehow stochastic ideas.
Probability is like God's analog scale.
Yeah, so I think both in terms of software engineering, right, probabilistic programming languages like Church, as well as in the hardware world where we are learning to work with these kind of systems better, right, to tolerate errors better through kind of system design rather than making every transistor perfect.
Yeah, that's something that probably you might want to look at. I'll send you some. Some reason I got into that conversation that where they are doing this so I'll send you some stuff on that.
Well, one of the things, and like this is probably a larger topic, so I'll just say something quickly, is that like because we use very dense representations in digital computers at the moment, if you jump from one part of your state space to another, it has an almost entirely different semantic meaning. Like if I was to flip the high bit in one word, then that could be a number like 4 billion times more than I would like it to be, which is really bad because semantically I don't want to like fire my rockets 4 billion times more. But then again,
but that also suggests that you shouldn't have every bit with the same reliability. Bits that are going to be flipped more often, you don't need them to have high reliability.
Oh yeah, it's like you take an image, you flip every low bit, it looks exactly the same, whatever. But I add something to that, which is that like a lot of error correcting codes, gray codes, et cetera, have this property that the state space is also then semantically compact in the sense that like a nearby state has a semantic interpretation which is similar to the other one. And it does seem like probably one of the reasons why neural nets, once you train them, are so resistant to noise is because they are a more kind of sparse distributed representation. So flipping one bit in that representation does give you a representation which is very semantically close. And that's something you want in a system which is going to be very thermodynamic in its operation, because it's like now you have a probability distribution over states. But so long as that probability distribution is like semantically coherent, it's like, wow, you're okay, you know? Yeah. In the sense that, like, if this thing says, is this a picture of a cat or not, then flipping individual bits inside.
Yeah, so graceful aging, maybe.
Well, it's that's one way to put it. I think that it's the high level goal, like the Desiderata
going
is
gracefully to failure, maybe sort of getting
Then,
closer and closer to phase transition.
Totally. And then what you want is that the like areas of state space which have one meaning are compact, because if your space has a lot of holes in it, and you can very easily go from one state which is a totally different meaning, that's bad. Yeah.
So going back to the DNA replication, do we know what the exact tau of E and R is? Like,
I think those numbers are known.
Yeah.
Yeah, I haven't plugged it in and tried something.
But that would be close to the theoretical lower bound, right? I mean, because that's a lot of data.
It's a lot of energy that the cell uses. Yes, that's a good point.
Yeah.
So, yeah, I would think so. So tau r may, so one has to understand the passive dynamics of that system also.
Yeah. Because from my understanding, there is actually a lot of, I mean, that's how we get point mutations, where we do get mistakes made in the copying process. So, you know, you don't have an exact zeroing up a bit. You sometimes may get a 0, sometimes may get 1, and mistakes happen.
So for example, HIV uses this as a feature. So what HIV does is, if it is in an environment that is hostile to it, so it's not getting enough energy and it needs to mutate fast, so it really makes more errors. It saves energy maybe by doing so, at least potential savings in energy, and then because it mutates more, it's creating more diversity in that.
Which then has a better evolutionary selection.
But okay, we could just do this back with the envelope. How many base pairs are there in a human genome? We should know this, you're a doctor.
So 1 gigabyte.
Well, there's 1 gigabyte of base pairs. Okay. So that's, what, around like 10, 2 to the 30, right? And then in a copy, I mean, the error rate seems to be like, what, like hundreds of base pairs or something?
It depends on like the environment, right? And it depends on the age as well. So like the older the cell is, the more errors you get.
Yeah, but typical, like, per
I can't tell you off the top.
But okay, but let's just say it's like order 2 to the 10. So that means we have a reliability of like 2 to the 20-ish, like 2 to the negative 20. Like
it's too fast for me.
Per copy, per copy, the chance that any individual base pair is corrupted is around 1 over 2 to the 20, I think. Which, I don't know. That's a super back of the envelope, right? And then if we plug that in, I guess, how much energy we
20.
What's that?
You got 20 KT out of there. I don't know how you did it.
Yeah. Well, that's tau. I'm saying tau r is 1 over 2 to the 20.
If you have 1 replication per second.
Yeah, true. And then, I mean, I guess it seems like one. Okay. So, we're building a computer and we want it to be thermodynamic. And so we want it to be efficient. And right now we seem to be very, very, at least if you do a naive analysis, you seem to be very, very high above the bound. Then what we're saying is that bound seems ultra loose because we're just not taking into account reliability.
I'm not sure the bound is, So I think that computers use so much energy because they are so reliable and they don't need to be quite so reliable.
Yeah, and that could actually be like the major source of.
Yeah. And in fact, so people who do computer architecture, they recognize this. They know that, it's the irreversibility that is the cost.
And the reason why the irreversibility costs you so much is that basically you have to have the whole thing just be very, very hot, and it has to be sitting on this like giant heat bath to make that happen.
Sorry, what has to be hot?
Just the whole system. Like you just really have to pound it with electrons just to.
Well, if you want it to be fast and correct, then you have to.
Fast and correct.
Yeah, it's just like every clock cycle, you have to squirt enough electrons in to make sure that like all the state changes are pushed forward.
Just gave me a good title for a book, Fast, Hot and Correct.
And on that note,
have you here. Really enjoy it. So thanks a lot again.